Welcome to the Deep Sleep Science Channel. Tonight, we're exploring one of the quietest, most powerful ideas in all of nature: how stars are born. If you enjoy these calm science journeys, you can gently like, subscribe, or leave a comment now before sleep starts to win. A star begins as a cold, dark patch inside a giant cloud of gas and dust. Over time, gravity gathers that material closer and closer together, while the cloud cools by releasing energy as light, mostly in infrared, because dust hides the process from visible view. As the cloud collapses, it spins faster, and that rotation naturally shapes a disk around the forming star. The young star, still called a protostar, grows by pulling in material from this disk, and at the same time, it sends some material back out through jets and winds, which help remove extra spin and reshape the surrounding cloud. Eventually, when the center becomes hot and dense enough, hydrogen fusion ignites. That's the moment a true, stable star switches on, no longer powered mainly by falling gas, but by nuclear energy in its core. And across the galaxy, this cycle repeats. Clouds become cores. Cores become protostars. Protostars become stars, while the light and energy from newborn stars slowly change the clouds around them, making space ready for the next generation. The places where star birth is most active are usually molecular clouds thick, cold reservoirs where much of the hydrogen is paired up as molecular hydrogen, H2. Hydrogen is the main ingredient, but the special thing is the environment. It's dense, shielded, and cool enough that the gas can stay together instead of being torn apart by harsh radiation. Tiny dust grains inside those clouds play a surprisingly protective role. They absorb and scatter ultraviolet light that would otherwise break molecules apart, and they help keep the cloud's interior chemically rich. In a way, dust acts like a dim curtain, allowing complex molecules to survive in the quiet middle of a cloud. Molecular clouds are cold by everyday standards, often only tens of kelvins above absolute zero. At those temperatures, the gas doesn't have much thermal energy to push back outward, so pressure support is weaker. That low temperature makes it easier for gravity to slowly gather the material into denser and denser pockets. A key guideline astronomers use is the GEMS idea, which links gravity, temperature, and density. If a clump of gas is large or massive enough, and cool and dense enough, then gravity can win, and the clump becomes unstable. In simple terms, it's a way of asking, is this gas region more likely to hold itself up, or to begin collapsing inward? Inside real clouds, turbulence adds a gentle kind of chaos. Swirling motions can help resist collapse by stirring the gas and creating extra internal support. But the same turbulence can also compress gas in certain places, making small regions denser than their surroundings, and those compressed pockets can become the starting points for collapse. Many star-forming clouds are threaded with long filaments, like faint, elongated strands. Dense cores where individual stars may eventually form often sit along these filaments, almost like beads on a string. This filamentary structure matters because it concentrates mass and can guide how the cloud breaks up into smaller pieces. When astronomers measure filaments in nearby star-forming regions, they often find a typical width on the order of about 1/10 of a parsec. That's a small fraction of a light year, but still enormous on human scales. The fact that many filaments share a similar width hints that common physical processes shape them across different clouds. Not every filament is equally productive. The densest filaments are the ones most likely to fragment into prestellar cores, which are the immediate seeds of future stars. These cores represent places where the cloud's material has become concentrated enough that collapse is becoming a real possibility. In several studies using Herschel data, many candidate prestellar cores are found very close within, roughly 0.1 parsec, the crest of the nearest filament. That pattern suggests that filaments are not just decorative shapes, they are central pathways that gather material and nurture the densest pockets. Being near the filament's spine often means being near the deepest part of its gravitational well. A prestellar core is a dense condensation that has not yet formed a central protostar, but it is already on the path toward collapse. It can be cold, dark, and quiet, with most of its light hidden by dust. Even so, it contains the structure and mass that can eventually become a new star. When collapse begins, gravitational potential energy doesn't disappear, it transforms. As material falls inward, some of that energy becomes heat and some is radiated away. This conversion is one reason a forming protostar can shine even before nuclear fusion truly turns on. As gas falls inward, it tends to conserve angular momentum, the same principle that makes a spinning figure skater rotate faster when pulling in their arms. As the infilling material shrinks toward the center, its rotation speeds up. This spinning motion strongly influences the shapes and structures that form around the newborn star. Rotation encourages the collapsing material to flatten into a disk rather than falling straight in from all directions. Over time, that becomes a circumstellar accretion disk, a rotating reservoir that feeds the growing object. This disk is also the birthplace of many later structures, including the raw ingredients for planets. The central forming object is called a protostar, while it is still gaining most of its mass from surrounding infall. It is not yet a stable main sequence star, but it is already a concentrated, warming center. Much of its growth happens as the disk and envelope continue delivering material inward. In early phases, a protostar's brightness can be dominated by accretion energy rather than nuclear fusion. As gas lands onto the protostar, it releases energy because falling into a deeper gravitational well converts motion into heat and radiation. This means a very young object can glow strongly even before it has the steady furnace of hydrogen burning. Astronomers often classify young stellar objects by their infrared emission because infrared light is excellent at slipping through dusty regions. The more surrounding dust and gas remains, the more the object's energy is absorbed and re-emitted as infrared. So the infrared signature becomes a practical way to tell how embedded and youthful a forming star still is. The Class 0 category is used for extremely young protostars that remain deeply buried in their natal envelopes. At this stage, the envelope is still massive and thick, and the protostar is hard to see directly. Most of what we detect is the dust and gas glowing gently in longer wavelengths. Class 0 objects are powered mainly by infall and accretion, not by sustained hydrogen fusion. Their central regions are still assembling, and the main energy source is the gravitational energy released as material continues to fall inward. In a calm way, they are still more in the making than fully lit from within. Class 0 lifetimes are often described as tens of thousands of years, which is brief compared to the full life of a star, but long compared to human history. It's a phase where dramatic change happens slowly, step by step, as the envelope reorganizes and the central object becomes more defined. Over that time, the protostar gathers mass and begins to shape its surroundings with outflows. Accretion onto a protostar is not necessarily steady, and it can happen in bursts. Instead of a smooth, constant flow, the disk can store material and then deliver it in sudden episodes. These bursts can brighten the system and temporarily change the temperature and chemistry of the surrounding disk. A few Orionis-type eruptions are among the most dramatic examples of these accretion outbursts, seen in some young stars as huge increases in brightness. They are like sudden surges of feeding from the disk onto the star. Because they can last a long time, they may represent major growth spurts in a star's early life. During FU Orionis events, Inferred accretion rates can jump by orders of magnitude compared with quieter phases. That means the young star can gain mass much faster for a while, as the disk rapidly funnels material inward. This helps explain how a star can assemble its final mass, even if it spends much of its youth looking relatively dim. Outflows and jets are commonly associated with active accretion, linking mass inflow to mass loss. As the system feeds the central object, some material is launched outward along the rotation axis, forming bipolar flows. This balance some gas falling in, some being pushed booties, one of the defining rhythms of star birth. Jets help remove angular momentum from the star disk system, which is crucial because too much spin would prevent continued accretion. By carrying away angular momentum, jets allow gas in the disk to spiral inward rather than staying stuck in orbit. In that sense, jets are not just byproducts, they help the whole system continue evolving. Star formation is not only about individual stars, it often produces clusters rather than isolated objects. When a large gas structure fragments, it commonly makes many dense cores at once, and a group of stars begins to grow together. These shared birthplaces shape how stars interact, how disks survive, and how early evolution unfolds. Many stars likely form in multiple systems binaries, and higher multiples because fragmentation and disk dynamics often make more than one bound object. A collapsing region can split into two or more centers, or a disk can become unstable and form companions. This is one reason the night sky contains so many paired stars. Feedback from newborn stars' radiation, winds, jets, and eventually supernova can both inhibit and stimulate further star formation nearby. It can blow gas away and shut down collapse in one direction, while compressing gas and encouraging new cores in another. Star birth, in this way, shapes the environment that will decide what happens next. Supernova shocks can compress clouds and potentially trigger new core formation, creating patterns where star formation spreads through a region over time. The shockwave can squeeze gas into denser layers, and if those layers cool and fragment, new stars can appear. This links the end of massive stars to the beginnings of later generations. On galactic scales, intense bursts of star formation can occur during galaxy interactions that compress and destabilize gas. When galaxies pass close or merge, their gravity can drive gas inward and create dense regions where many stars form rapidly. These events can light up whole galaxies with the glow of newly born stars. Spiral density waves in galaxies can organize gas into spiral arms, where compression encourages star formation. The arms are not just visual patterns of stars they often trace, places where gas is denser and more prone to collapse. As gas flows through these regions, it can be squeezed enough to form new stars. Cloud-cloud collisions are another idea discussed in some regions. When two molecular clouds meet, their gas can be compressed at the interface. That compression can raise density quickly and create conditions favorable for collapse. In some places, this may help explain unusually intense or localized star formation. Triggered star formation is not the only pathway many stars form spontaneously in turbulent, self-gravitating clouds. In that picture, the cloud's own internal structure and motions naturally create dense regions that collapse without a clear external push. Both triggered and spontaneous processes can occur in the same galaxy, and sometimes in the same cloud. A common big-picture view is hierarchical: large cloud, then filaments, then dense cores, then protostars, then young stars. Each step is a narrowing of scale, as gravity focuses material into smaller and denser structures. Observations across many wavelengths support this layered progression, even though details vary from region to region. Star formation is strongly linked to the density structure of gas. Denser gas tends to be more closely associated with active star birth. A cloud can contain a lot of mass, but if most of it is not in dense regions, star formation may remain modest. This is why maps of dense gas are often better predictors of star-forming activity than maps of total gas alone. Many nearby star-forming clouds show that only a small fraction of the total cloud mass sits in the densest core-forming filaments. Most of the cloud can be more diffuse and not immediately participating in collapse. This helps explain why star formation efficiency is often low. Only a small portion of the raw material is in the right state at the right time. Magnetic fields thread molecular clouds and can provide support against collapse by coupling to partially ionized gas. Even when the ionization fraction is tiny, it can allow magnetic forces to influence the bulk motion of the gas. This means star formation is shaped not only by gravity and pressure, but also by invisible magnetic structure woven through the cloud. Ambipolar diffusion describes how neutral gas can drift relative to ions that are tied more strongly to magnetic fields. Over time, neutrals can slowly slip inward, even when magnetic support is present. In some theoretical frameworks, this gradual drift helps regulate how quickly a magnetized core can contract. Cooling is essential because collapsing gas must shed heat to keep contracting and fragmenting. At low temperatures, finesse structure lines and molecular rotational lines can radiate energy away efficiently. Without cooling, the gas would heat up too much as it compresses, increasing pressure and resisting further collapse. Dust grains do more than block ultraviolet light. They also provide surfaces where simple molecules can form and where ices can accumulate. In cold regions, atoms and molecules can stick to grain surfaces, react, and build up icy mantles. This grain surface chemistry becomes an important pathway for forming compounds that are hard to create in the cold gas phase alone. Carbon monoxide, KO, is widely used as a tracer of molecular gas because molecular hydrogen is difficult to observe directly in cold clouds. CO emits radiation in rotational transitions that can be measured, helping astronomers map where molecular material is located. By tracking CO and related molecules, researchers can infer cloud structure, motions, and mass distribution. In very cold, dense cores, CO can freeze out onto dust grains, changing the gas phase chemistry and the cloud's ability to cool. When CO leaves the gas phase, the remaining gas can behave differently, both chemically and thermally. This freeze-out also helps build up the ice layers that later evaporate and enrich warm regions near protostars. The distribution of newly formed stellar masses is summarized by the initial mass function, or IMF. It describes statistically how many low-mass stars form compared with high-mass stars in a given population. Because stellar mass controls brightness, lifetime, and feedback strength, the IMF is one of the most important big-picture outcomes of star formation. A classic description of the IMF at higher masses is the salpeter form, often expressed as a power law with a slope near 2.35 in a common convention. That slope implies that massive stars are much rarer than low-mass stars. Even so, the rare massive stars can dominate energy output and chemical enrichment because they are so luminous and short-lived. Modern IMF parameterizations, such as Krupa or Chabrier, include a flattening at lower masses compared with a single salpeter slope. This reflects evidence that the distribution does not keep rising as steeply toward the lowest masses as a pure power law would suggest. It's a reminder that different physical processes may shape the low-mass and high-mass ends. Some research debates whether the IMF is universal or varies with environment, temperature, or metallicity. In hotter gas, for example, the characteristic mass scale for gravitational instability can increase, which might favor forming more massive objects. In lower metallicity gas, reduced cooling and dust content can also change how fragmentation proceeds. The very first stars, often called population 3, formed in metal-free gas, made almost entirely of hydrogen and helium. Without metals and dust, early star formation relied heavily on molecular hydrogen for cooling, and the balance of processes was different from today. Many models suggest these first stars tended to be more massive, highly luminous, and short-lived, strongly influencing early cosmic chemistry. Metal enrichment from the first supernova changed what came next by introducing heavy elements that enable more efficient cooling and dust formation. With better cooling, gas can fragment into smaller pieces more readily, supporting the formation of lower-mass stars. This gradual transition from pristine to enriched star formation helped shape the long-term evolution of galaxies. On cosmic timescales, the universe's overall star formation rate rose to a peak at intermediate redshifts and then declined toward the present. That broad history reflects changing gas supply, galaxy growth, and feedback processes. It also means that the conditions for star birth density, metallicity, radiation fields have varied across cosmic time. The continuous cycling of gas into stars and back into the interstellar medium through winds and supernova drives galactic chemical evolution. Each generation of stars slightly reshapes the composition of the gas that future stars will form from. Over billions of years, this recycling builds up the chemical diversity that later becomes planets, atmospheres, and complex chemistry. As protostars grow and change, their thick surrounding envelopes gradually thin out, and more of the central system becomes visible. In the earliest stage, dust and gas wrap the forming star so completely that most of what we detect is reprocessed infrared and millimeter light. Over time, as material falls inward, is blown outward, or is heated and dispersed, the envelope becomes less dominant. That is why later-stage young stars can be seen more clearly at shorter wavelengths, intruding near-infrared and even optical light in favorable cases. Astronomers often describe low-mass star formation with a simple observational sequence: class 0 to class 1 to class the 2nd to class the 3rd. This is not a perfect age ruler, but it's a useful way to connect what we observe to how much surrounding material remains. The general idea is that the system starts deeply embedded, then gradually reveals a disk-dominated young star, and finally becomes relatively free of its original dusty cocoon. Even when the sequence applies, real objects can move through it at different speeds depending on environment and accretion history. Class 1 protostars still carry substantial envelope material, but they often show clearer signs that a disk is becoming the main structure feeding the star. The envelope is still important, yet it is no longer the only defining feature, and outflow cavities may allow more light to escape. Because of this, Class 1 sources can appear brighter at shorter infrared wavelengths than the youngest Class 0 objects. They are still actively assembling, but the system is beginning to look more like a star plus disk, rather than an envelope-dominated core. Class. The second objects are often associated with classical T Tauri stars, where a prominent circumstellar disk is usually present, but the original envelope has mostly faded. These systems can show strong signatures of ongoing accretion from the disk, such as emission lines and excess infrared light from warm dust. The disk may still be massive enough to form planets, grow dust, and develop internal structure. In many regions, Class the 2nd is the stage where young stars are most numerous and easiest to study in detail. Class. The third objects are typically much more disk-poor than Class the 2nd objects, approaching the appearance of a relatively naked young star. The star may still be young and magnetically active, but it no longer shows strong infrared excess from a thick, dusty disk. Some Class the 3rd stars keep only tenuous debris or a very thin remnant disk, while others have cleared their disks almost entirely. This stage signals that the gas-rich disk phi so important for both star growth and planet formation is largely coming to an end. One common reason protostars glow so strongly in the infrared is that dust acts like a blanket that absorbs energetic light and re-radiates it at longer wavelengths. The central protostar and inner disk can emit higher energy photons, but the surrounding dust intercepts much of that energy. Dust then warms up and releases the energy as thermal infrared radiation, which can travel out more easily. This is why deeply embedded young stars may be faint in visible light yet bright in infrared surveys. Bolometric temperature is one tool astronomers use to estimate a young object's evolutionary state by looking at how its total energy is distributed across wavelengths. If most of the energy emerges at long wavelengths, the bolometric temperature tends to be low, often suggesting a more embedded stage. As envelopes thin and warmer inner regions become more visible, the spectrum shifts toward shorter wavelengths and the bolometric temperature rises. However, this measure can be uncertain as a strict clock because viewing angle, cavity geometry, and variability can all change the observed spectrum without changing the true age by the same amount. Protostellar envelopes are often clumpy and asymmetric rather than smooth and uniform, and that matters for what we see. If there are gaps or lower density paths, especially along outflow cavities, radiation can escape more easily in certain directions. This can make two similar objects look very different simply because we view them from different angles. Clumpiness also influences chemistry and temperature, because dense pockets stay colder and more shielded, while thinner areas heat and disperse more quickly. Episodic accretion is often used to help explain why many protostars appear dimmer than simple steady-growth models predict. If a protostar spends long periods accreting slowly, it can look faint much of the time. Then, during short bursts, it gains a lot of mass quickly and brightens dramatically. This bursty pattern can reconcile the idea that stars still build up to normal masses, even if they do not appear consistently luminous in snapshots of star-forming regions. In FU Orionis events, inferred accretion rates can leap by orders of magnitude compared with typical quiet phases, meaning the star can gain mass much more rapidly for a while. Think of the disk as a reservoir that can sometimes become unstable and dump a large amount of material inward. When that happens, the energy released by the sudden infall makes the entire system brighten strongly. These events may represent rare but important growth spurts that contribute noticeably to a star's final mass. FU Orionis systems can brighten over years and then remain unusually luminous for long periods before fading. This slow, sustained behavior suggests the disk has entered a prolonged high accretion state rather than a momentary flash. Because these outbursts can last decades or longer, they can reshape the disk's temperature structure and the conditions under which dust and gas evolve. Even after the system dims, the disk may carry chemical and structural memory of the burst. Accretion bursts can heat disk material enough to change dust mineralogy, including increasing the crystallinity of silicate grains. Under calmer, colder conditions, many silicates remain in more amorphous forms. When temperatures rise sufficiently, atomic arrangements can reorganize into crystalline structures, changing the dust's physical and optical properties. This matters because dust is the raw material for planet building, and its structure affects how it sticks, settles, and interacts with radiation. Some JWST-related work has reported direct evidence consistent with silicate crystallization happening within a disk during an episodic accretion burst. The key idea is that a burst can provide the heat needed to transform dust locally, right where it resides, rather than requiring crystals to be transported from hotter inner regions. If this happens, then bursts are not just brightness, events they can actively rework the building blocks of planets. It also means that disk mineralogy may not reflect a slow, steady history, but a story punctuated by occasional thermal upheavals. Disk heating during bursts can also change where ices sublimate, shifting chemical boundaries within disks. Many important molecules exist as ice on dust grains in cold outer regions, but become gas when warmed. When a burst raises temperatures, the snow lines for different volatiles can move outward, temporarily turning ices into vapor over a larger region. That can change what chemistry is active and how efficiently solids grow, because ice coatings strongly affect how grains stick together. The tight collimation of many jets, how narrowly focused they are, points strongly toward magnetic processes in the star disk system. In many models, magnetic fields act like guiding rails that channel plasma and gas along field lines, producing narrow beams rather than broad winds. The disk's rotation and magnetic fields can work together to launch and shape these flows. Collimation is one reason jets can travel long distances and still maintain relatively coherent structure. Many jet-driven shock features are observed as Herbig-Haro objects near young stars, marking where fast outflows collide with surrounding material. These shocks heat the gas and make it glow, often producing bright knots and arcs. Each feature is a visible sign of energy being deposited into the surrounding cloud. In a larger sense, they show that star formation is not only about gathering material inward, but also about pushing and sculpting the environment outward. Herbig-Haro objects are bright patches of nebulosity created when fast jets slam into gas and dust in the surrounding region. The collision produces shock waves that compress and heat the material, exciting atoms and molecules so they emit light. Because these shocks trace where the jet is actively interacting with its environment, they are like signposts of a young star's recent activity. Even if the protostar itself is hidden, the HH objects can reveal that powerful outflows are present. HH objects can change measurably over human timescales because shocks propagate, brighten, and fade as they move through an uneven medium. Dense clumps brighten when they are struck, then dim as the shock passes and conditions change. This means astronomers can sometimes watch the evolution of an HH flow over a few years or decades, which is unusually fast in astronomy. Such changes help estimate velocities and reveal how variable the jet has been. HH features are often aligned with a young star's rotation axis, reflecting the bipolar geometry of ejection. Because the disk forms in the equatorial plane, outflows tend to emerge perpendicular to that plane, along the system's poles. This alignment helps connect jets directly to the disk and to the star-disk interaction region, where launching is thought to occur. It also means that mapping HH objects can tell you the orientation of the hidden disk system. Jet speeds in HH systems can be hundreds of kilometers per second, fast enough to cross enormous distances in relatively short astronomical times. At those speeds, the outflow carries substantial momentum and can strongly disturb nearby gas. Such high velocities are part of why shocks form so readily when jets run into slower-moving or stationary cloud material. The speed also implies that the launching region is deep in the gravitational potential of the star disk system, where large energies are available. HH objects are typically transient on astronomical timescales, often lasting tens of thousands of years rather than millions or billions. They exist during the active accretion and outflow phases of a young star's life, when strong jets are being produced. As the star matures and accretion weakens, jets fade and the shock structures disperse. So HH objects are brief signatures of youth, tied to a formative window rather than the star's long adulthood. Some HH jets extend for parsecs, indicating sustained ejection over long intervals. A parsec is more than 3 light-years. so a parsec-scale jet is an enormous structure driven by a relatively small central object. Long jets imply either continuous outflow for a long time or repeated episodes that keep adding momentum in the same direction. They show that the influence of a forming star can reach far beyond its immediate disk and envelope. HH emission often traces partially ionized gas heated in shocks. When a shock passes, it can rip electrons from atoms and raise temperatures enough for specific emission lines to appear. The mixture of neutral and ionized material gives HH objects their characteristic spectra and helps diagnose shock speeds and densities. By studying this emission, astronomers can infer conditions that would otherwise be invisible in cold, dark cloud material. Because dust obscures optical light, many embedded jets are more easily revealed in infrared or radio tracers than in visible observations. In deeply buried regions, optical photons can be absorbed or scattered away before they ever escape the cloud. Infrared light and radio emission can pass through dust more effectively, allowing astronomers to trace the jet closer to its source. This is why multi-wavelength observations are essential for building a complete picture of outflows in the earliest phases. Molecular outflows can accompany jets, showing wider-angle swept-up gas, in addition to the narrow, fast central component. The jet can plow into surrounding material and entrain it, pushing a broader flow outward that is cooler and more molecular. These outflows can be mapped with molecular lines and can carry large amounts of mass compared with the jet itself. Together, the jet and the molecular outflow show both a sharp driving beam and a wider environmental response. Observational studies often treat jets as a kind of fossil record of recent accretion and ejection history. If the jet has knots, bends, or repeated shock features, those can correspond to changes in ejection speed or direction in the past. By measuring distances and motions of knots, researchers can estimate when different episodes occurred. In this way, the outflow becomes a time-encoded trail of the young star's recent growth behavior. Massive protostars can also launch powerful jets, although the full details of massive star formation remain an active research area. In HEMAS environments, the stakes are higher because radiation pressure and ionization can interact strongly with inflow. Even so, jets appear to be common, suggesting that disk-mediated accretion and magnetically influenced ejection may be important across a wide range of stellar masses. Massive jets also inject tremendous energy and momentum into their surroundings, shaping entire regions. Some of the longest and fastest protostellar jets reported are associated with massive protostars and Fleet phenomena. HEMAS systems can provide large accretion rates and strong gravitational potentials, which help power fast outflows. When such jets remain collimated over long distances, they can carve large cavities and create dramatic shock structures far from the source. These extreme jets demonstrate that even in turbulent, crowded environments, a young system can maintain a coherent outflow channel. In HEMAS environments, ionizing radiation can interact strongly with accreting filaments and the surrounding cloud structure. As a massive protostar brightens, it emits ultraviolet photons that can ionize nearby gas. Ionized gas behaves differently. It is hotter, more pressurized, and can expand outward. Whether accretion continues depends on how inflow geometry, density, and gravity compete with the expanding influence of ionization. H2 regions form when ultraviolet radiation from hot, young, massive stars ionizes surrounding hydrogen gas. Ionization strips electrons from hydrogen atoms, creating a plasma that glows and emits characteristic spectral lines. The gas temperature in an H2 region is much higher than in the cold molecular material around it, which creates strong pressure differences. This is one reason H2 regions can expand and reshape their environments. The classic Strömgrundsfär concept describes an ionized region where the rate of photoionizations is balanced by the rate of recombinations. If a star emits a steady stream of ionizing photons, there is a radius within which ionizations keep up with recombinations in the gas. Inside that boundary, the gas remains mostly ionized. Outside it, the gas stays mostly neutral. While real regions are far messier than perfect spheres, the concept provides a helpful baseline for understanding ionized bubbles around young massive stars. As LH, the second region, expands, it can push on adjacent neutral gas, altering local pressures and densities. The hot ionized plasma exerts outward pressure, driving a front into cooler surrounding material. This can compress neutral gas into shells and ridges, potentially changing where new dense cores might form. Over time, expansion can also disperse gas and reduce the supply available for further accretion nearby. One proposed triggering mechanism is collect and collapse, where an expanding ionized bubble sweeps up a dense shell that later fragments. First, the expansion gathers neutral material into a compressed layer. Then, if that layer becomes massive enough and cool enough, gravity can cause it to break into tumps that collapse into new stars. This is one way star formation can appear around the edges of an H, the second region, potentially creating new generations. Pillar-like structures can form as radiation erodes less dense gas, leaving denser clumps behind as elongated columns. Imagine a cloud with uneven density. UV radiation and winds chew away the softer, lower-density parts more quickly. The denser sections survive longer, and as material around them is removed, they stand out as pillars. These pillars can sometimes contain embedded young stars or dense cores still resisting erosion. Numerical simulations show that ionization front dynamics in structured clouds can create complex rims, pillars, and globules. When the surrounding medium is clumpy, the ionization front does not advance uniformly. Instead, it wraps around dense pockets, creates curved, bright edges, and drives shock compression in complicated patterns. Simulations help explain why real star-forming regions often look sculpted rather than smooth, with sharp boundaries and intricate shapes. Observations around some galactic H, the second regions, are widely discussed as being consistent with collect and collapse triggering in certain cases. Researchers look for evidence such as dense swept-up shells, clusters of young objects near the shell, and age gradients that match the expansion history. However, the best supported cases usually combine multiple lines of evidence rather than relying on appearance alone. When the evidence does line up, it suggests that massive stars can, in some environments, help initiate the birth of additional stars around them. Carbon monoxide, usually just called CO, is one of the most important tools astronomers use to see molecular clouds because the main molecule, H2, is very hard to detect directly when it is cold. CO has rotational transitions that emit at radio and millimeter wavelengths, and those photons can escape from many parts of a cloud. By mapping CO emission, astronomers can trace where molecular gas is, how it moves, and how it is structured. Even though CO is not the most abundant molecule, it acts like a readable tag attached to otherwise invisible hydrogen. In very cold, dense regions, CO does something subtle but important. It can freeze out of the gas and stick to dust grains. When that happens, the amount of CO in the gas phase drops, which changes both the chemistry and the cooling behavior of the core. SEO is also a coolant, so removing it from the gas can affect how easily the core sheds heat as it contracts. Freeze-out is one reason dense core chemistry can look very different from the chemistry of more diffuse molecular gas. At the low temperatures typical of dense cores, certain kinds of emission lines become the main radiators that let gas lose energy. Thinner structure lines from atoms and rotational lines from molecules can carry heat away by emitting photons of specific wavelengths. This is crucial because collapsing gas needs a way to cool, otherwise it heats up, pressure rises, and the collapse slows. In practice, the ability of gas to cool through line emission helps determine how small a collapsing region can fragment into. Cooling is not just a detail. It is a main reason clouds can continue collapsing and also break into many smaller pieces. When gas compresses, it naturally warms, but if it can radiate that heat away, it stays relatively cold. Staying cold keeps pressure from rising too much, which makes gravity's job easier. This is one of the quiet reasons star-forming regions can turn a large cloud into many individual stars instead of one giant object. Magnetic fields run through molecular clouds, and even though we cannot see them directly with our eyes, we can detect their influence on gas. Because a small fraction of cloud material is ionized, magnetic fields can couple to that ionized component, and through it, affect the motion of the mostly neutral gas. This can add an extra kind of support against gravity, slowing or reshaping collapse. The result is that star formation is not only a contest between gravity and thermal pressure, but also a negotiation with magnetism. Ambipolar diffusion is a process where neutral particles drift relative to the ions that are more tightly tied to magnetic field lines. In a dense cloud, most of the mass is neutral, but the magnetic field holds onto the ions. Over time, neutrals can slowly slip inward, while ions lag behind, allowing collapse to proceed even in magnetized environments. This is one mechanism that can regulate the pace of contraction in some theoretical pictures, making collapse more gradual than a simple freefall. In some frameworks, ambipolar diffusion acts like a slow-release valve on star formation, controlling how quickly a magnetized core can concentrate its mass. If magnetic support is strong, collapse may be delayed until enough neutral material has drifted inward to overcome the field's support. This can change the timeline of core evolution and may influence the sizes and shapes of the structures that form. Whether ambipolar diffusion dominates depends on local conditions like ionization level, density, and field strength. Turbulent motions in clouds do not last forever, they can decay, and where they lose energy, gas becomes more vulnerable to gravity. Turbulence can be thought of as internal stirring that provides extra support against collapse. But turbulent energy can dissipate through shocks and interactions, especially in dense regions. Where that dissipation happens, gas can settle, become denser, and more easily begin collapsing. Some star formation scenarios connect filaments to magneto-hydrodynamic turbulence, where gas motions and magnetic fields shape long, dense strands. In that view, turbulence and magnetic forces naturally produce filament networks, and the densest parts of those filaments later become gravitationally unstable. This matters because it links large-scale cloud dynamics to the small-scale birthplaces of stars. Filaments are then not accidental shapes, but outcomes of how magnetized gas moves and compresses. The sonic scale idea links filament widths to the transition between supersonic turbulence and subsonic motions in cold gas. On large scales, motions can be faster than the sound speed, creating shocks and strong compressions. At smaller scales, turbulence can become gentler and subsonic, changing how structures settle and persist. If filament widths reflect this transition scale, it suggests a deep connection between turbulence physics and the characteristic size of star-forming filaments. Dense cores can sometimes be described, at least approximately, with density profiles similar to pressure-bounded spheres. This is a simplified way to represent a core that is held together by gravity, but also confined by external pressure from surrounding gas. Such models help astronomers interpret observations and estimate stability, whether the core is likely to collapse or remain supported. Real cores are rarely perfect spheres, but these idealized profiles can still capture useful aspects of their internal structure. When collapse proceeds, infoul can sometimes be detected through spectral line asymmetries that indicate inward motions. If gas is falling toward the center, the absorption and emission along the line of sight can shift in a way that makes one side of a spectral line stronger than the other. This is a subtle measurement, but it provides a direct clue that material is moving inward rather than simply swirling or sitting still. Different molecules trace different densities, so observers often compare multiple lines to build a clearer picture. Protostellar disks transport angular momentum outward, which is essential for allowing mass to move inward onto the star. Without a way to shed angular momentum, gas would remain in orbit and would not accrete efficiently. Disk transport can occur through turbulence, waves, magnetic stresses, or large-scale instabilities. In effect, the disk acts as a mediator. It takes rotating material and gradually reorganizes it, so some can fall inward while angular momentum is redistributed outward. Disk turbulence and instabilities can make accretion time variable, including in the form of bursts. Instead of a smooth, gentle inward flow, the disk can build up mass in certain regions and then release it more suddenly. Instabilities can arise from gravitational effects, changes in ionization, or temperature-dependent behavior that alters how well gas couples to magnetic fields. This is one reason young stars can show periods of relative quiet followed by dramatic brightening. In clusters, close encounters between young stars can truncate disks, cutting off outer regions and reducing disk mass. When stars form near each other, their gravity can disturb neighboring disks, stripping material or reshaping disk edges. This can affect how long accretion can continue and how much material remains for planet formation. The same star born in a crowded cluster can therefore have a very different disk history than a similar star born in isolation. Disks evolve through viscous spreading, winds, and planet formation, and each of these processes changes how the disk feeds the star. Viscosity more generally, internal stresses can cause disk material to drift inward, while the disk spreads outward. Winds can remove gas from the disk surface and carry angular momentum away. Meanwhile, falling planets can trap dust, open gaps, and redirect flows, changing the disk's structure and its accretion behavior. High-resolution millimeter observations can reveal rings, gaps, and other substructures that suggest dust growth and redistribution. Millimeter wavelengths are especially good for tracing larger dust grains pebbles and millimeter-sized particles that are important for building planetesimals. When astronomers see rings and gaps, they interpret them as places where particles pile up or are depleted. These patterns can be shaped by forming planets, but they can also come from purely physical changes in gas pressure and temperature. ALMA has produced especially detailed disk images, making it possible to study fine ringed structures at remarkably small scales. By combining many antennas, ALMA achieves the resolution needed to see patterns that were once only theoretical. These images show that disks are not smooth pancakes of dust and gas. They are structured environments. That structure matters because it affects where solids concentrate and where planets may form most efficiently. Disk rings can arise from several mechanisms, not only from planets. Pressure bumps in the gas can trap dust and create bright rings without any planet being present. Condensation fronts where certain molecules freeze out can change dust sticking and opacity, also encouraging ring-like features. This is why interpreting rings requires multiple lines of evidence, including gas kinematics and multi-wavelength dust measurements. Snowlines mark the disk radii where specific volatiles transition between ice and vapor, and this has strong effects on both chemistry and dust behavior. Icy grains can be stickier and can grow more efficiently, while vapor regions behave differently and can replenish gas phase molecules. Snowlines also change how much solid material exists at different radii, which influences where planet-building materials concentrate. In observations, snowlines can sometimes be inferred from chemical traces that change abruptly across those temperature boundaries. Water snowlines are especially important because water ice can dramatically affect grain growth and disk opacity. Where water is frozen, grains gain an icy coating that can help them stick during collisions. Water also carries a significant fraction of oxygen, so its phase affects disk chemistry in a major way. The location of the water snowline depends on luminosity and accretion heating, so it can shift as the star evolves. Carbon monoxide snowlines occur farther out in many disks, because CO freezes at lower temperatures than water. This means CO can be icy in outer disk regions while remaining a gas closer in. The CO snowline helps set where certain carbon-bearing reactions happen and influences what molecules are available in gas form. It also affects which traces astronomers use to map disk gas, because CO-based lines behave differently depending on whether CO is frozen out. Dust grains grow from tiny submicron particles to larger pebbles through collisions and sticking, which is a key early step in making planets. Early grains are so small they follow the gas closely, but as they grow, they begin to drift and concentrate. Growth is not guaranteed. Collisions can also fragment grains, so the balance of sticking versus breaking depends on speeds, composition, and ice coatings. The growth process is central because solid bodies must form before planets can assemble. Dust settling toward the disk midplane increases density there, creating a thinner, denser layer of solids. As grains settle, the midplane becomes a preferred place for further growth because particles collide more often. A dense midplane can also trigger instabilities that rapidly concentrate solids into clumps. This settling is one reason disks become vertically structured, a puffier gas component above and a flatter dust-rich layer below. In LOMA systems, magnetospheric accretion channels gas along magnetic field lines from the inner disk to the stellar surface. Instead of falling straight from the disk plane, material can be lifted and guided along field lines and then crash onto the star near magnetic poles. This produces hotspots and shocks where the gas impacts the surface. It is one of the reasons young stars can have strong variability and distinct emission features. The truncation radius of a disk, the point where the star's magnetic field disrupts the inner disk, depends on magnetic field strength, accretion rate, and stellar properties. If accretion is strong, the inner disk can push closer to the star before being disrupted. If the magnetic field is stronger, it can keep the disk farther out. This boundary region is important because it sets where material transitions from orbiting in the disk to being magnetically funneled onto the star. Accretion shocks occur when infilling gas hits the stellar surface or dense inner regions at high speed, converting motion into heat and radiation. These shocks can emit in ultraviolet and X-ray wavelengths, adding to the energetic environment around the young star. They also influence local chemistry by producing ionizing photons that affect nearby gas. Observers study these shocks through specific spectral signatures and excess emission over what the stellar photosphere alone would produce. Young stars often have strong magnetic fields that power frequent activity, including flares. These fields are generated by internal motions and convection, and they can be stronger and more complex than the Sun's field. Strong fields couple the star to its disk and help launch winds and jets. They also shape the high-energy radiation environment, which can influence disk heating and chemistry. Magnetic reconnection events where twisted magnetic field lines snap and realign can heat plasma to extremely high temperatures. This is a key mechanism behind stellar flares and a major source of X-ray emission in young stars. When reconnection happens, stored magnetic energy is released rapidly, accelerating particles and producing radiation. These events add a time-variable high-energy layer to the star-forming environment. Protostellar X-rays can arise from multiple sources, including magnetic activity, reconnection flares, and accretion-related shocks. X-rays penetrate gas more deeply than ultraviolet light in some conditions, affecting ionization in disk surfaces and envelopes. Ionization changes how well gas couples to magnetic fields, which in turn influences turbulence and angular momentum transport. So X-rays are not just a byproduct, they can feed back into the disk's physical evolution. Accretion hotspots can rotate in and out of view, producing periodic or quasi-periodic brightness changes. When a young star has bright, localized impact regions from magnetospheric accretion, the star's rotation carries those spots around. Observers can detect repeating light curve patterns and use them to estimate rotation periods. This variability also helps diagnose how stable accretion is and how the magnetic geometry is arranged. Variability surveys in infrared and optical are powerful because they catch young stars in the act of changing. Infrared variability can reveal changes in warm dust emission or accretion heating, especially in embedded systems. Optical variability can trace spots, flares, and accretion signatures in less obscured stars. By monitoring many objects over time, astronomers build statistical pictures of how common bursts, dips, and cycles are in young populations. Jets can include internal shocks where faster ejecta catch up to slower material launched earlier. When the outflow speed varies, the later, faster stream collides with the earlier, slower stream, creating a shock front within the jet itself. These shocks often appear as bright knots that move outward over time. Studying them helps reveal how variable the launching engine is, and how changes at the star-disk interface propagate into large-scale structures. Time variability in jet knots can encode the history of episodic accretion over years to centuries. If knots are spaced at certain distances and their speeds are measured, astronomers can estimate how long ago different ejection pulses occurred. This turns the jet into a timeline stretched out in space. It is one of the rare cases in astronomy where we can reconstruct a young system's recent past from visible moving features. Because HH features can move quickly, repeated imaging can reveal measurable displacements across the sky. By comparing images taken years apart, astronomers can track proper motions and infer actual velocities when the distance is known. This provides direct kinematic evidence of fast outflows rather than relying only on Doppler shifts. Combining proper motions with spectra gives a more complete 3D sense of how the jet is moving. Knot spacing along jets can act like a rough clock for episodic ejection intervals, especially when distances and velocities are constrained. If knots appear at regular intervals, that can suggest repetitive outbursts or quasi-periodic variability in accretion and launching. If spacing is irregular, it can indicate more chaotic or burst-like behavior. Either way, the pattern offers clues about the inner engine that cannot be resolved directly. Some observed jets show chemical richness in the outflowing molecular gas, including molecules that are common in ices and organic chemistry. Shocks can liberate molecules from dust grains, heat gas to drive new reactions, and mix material from different regions. As a result, outflows can become chemically distinctive compared with the cold, undisturbed cloud. These chemical signatures help diagnose shock strength, density, and the history of interaction with the surrounding medium. Maser emission from molecules like water or methanol can trace shocked gas and dynamic processes in massive star-forming regions. A maser is a natural microwave laser that produces intense narrow emission lines under specific physical conditions. Masers are bright enough to be detected across large distances in the galaxy and can pinpoint compact, energetic sites. Their variability and motion can also reveal rapid changes and precise kinematics in regions that are otherwise hard to resolve. Submillimeter interferometry helps probe cold dust emission at high resolution, which is essential for separating disks from envelopes and measuring structure. By combining signals from multiple antennas, interferometers can achieve much finer detail than a single telescope. This allows astronomers to map where mass is concentrated and how it is arranged around the protostar. Such measurements are key for estimating disk sizes, disk masses, and the geometry of embedded systems. Spectral line observations can simultaneously trace infoul, rotation, and outflow, because different molecules are sensitive to different temperatures and densities. Some lines trace the cold envelope, others trace the warmer inner disk, and still others trace shocked outflow gas. By fitting Doppler shifts and line shapes, astronomers reconstruct motions that cannot be seen directly. This is how we infer the complex choreography of material falling in, swirling around, and being launched out. Polarization measurements of dust emission are a major way to infer magnetic field geometry in star-forming regions. Non-spherical dust grains can align with magnetic fields, causing their thermal emission to be polarized. By mapping the polarization direction across a cloud, astronomers estimate the projected orientation of the magnetic field. These maps help answer questions about whether fields guide filaments, resist collapse, or become tangled by turbulence. Ionization fractions in dense cores are typically very small, but they matter greatly because they control how well gas couples to magnetic fields. If ionization is too low, magnetic forces have less leverage over the bulk neutral gas. If ionization is higher, magnetic coupling strengthens, affecting ambipolar diffusion, magnetic braking, and turbulence behavior. This is why processes like cosmic ray ionization, even at low levels, have outsized importance in dense star-forming environments. Cosmic rays can penetrate deep into clouds and ionize gas even where starlight cannot reach. In the shielded interiors of dense cores, cosmic rays may be one of the main ionization sources. That ionization influences chemical pathways and helps maintain a small population of charged particles. In turn, those charges control magnetic coupling and can alter how gas collapses and how disks evolve. The balance between heating and cooling sets the temperature structure inside clouds and cores, and that balance depends on multiple energy inputs. Heating can come from compression, cosmic rays, and radiation fields, while cooling comes from line emission and dust interactions. Small changes in this balance can shift the gene's mass and fragmentation behavior. Temperature is therefore not just a background condition, it can reshape what kinds of stars form and how quickly collapse proceeds. Magnetic braking is a process where magnetic fields transfer angular momentum from rotating collapsing gas to the broader environment. If magnetic coupling is strong, the field can act like a brake pad, slowing rotation and potentially limiting disk sizes. This can influence whether a large disk forms early or whether the disk remains compact. Magnetic braking is one reason disk formation can vary significantly between regions and between different theoretical assumptions about ionization and field geometry. Disk sizes can also be influenced by turbulence and misalignment between rotation axes and magnetic fields. If the magnetic field is not aligned with the rotation axis, braking can be less effective in some circumstances, allowing a larger disk to form. Turbulence can also twist and redistribute angular momentum locally, changing how material settles. These effects help explain why observed disk radii span a wide range instead of clustering around one value. Large surveys show that young stellar objects in a single region can span a wide range of luminosities and inferred accretion rates. This spread suggests that star growth is not uniform. It likely involves variability and differences in environment. Some objects may be in quiet phases, while others are actively accreting or have recently experienced bursts. The diversity observed in large samples supports the idea that time-variable growth is a normal part of star formation. Because dust reddening changes colors, classification methods must carefully account for extinction along the line of sight. Dust absorbs and scatters blue light more strongly than red light, making objects look redder than they really are. If extinction is not corrected, a more evolved object could be mistaken for a more embedded one, or vice versa. Accurate classification often requires combining color information with spectral data and multi-wavelength observations. Young star catalogs often require careful cleaning for contaminants, especially background galaxies that can mimic the infrared colors of embedded young stars. At faint flux levels, distant galaxies can appear as red infrared sources and be mistaken for protostars if selection criteria are too simple. Astronomers use additional indicators such as spatial clustering, spectral shapes, and cross-matching with other wavelengths to reduce contamination. This careful filtering is important because incorrect members can distort inferred lifetimes, luminosity distributions, and star formation rates. Bolometric luminosity is a useful measure because it sums the total power emitted across all wavelengths, not just what is seen in one band. This matters for embedded objects because dust can shift energy from visible or near-infrared into far-infrared and millimeter light. By integrating across the spectrum, bolometric luminosity provides a more complete estimate of how much energy the system is releasing. It allows more meaningful comparisons between objects whose light is redistributed differently by dust. Gravitational freefall time becomes shorter as density increases, which means denser cores collapse more quickly than diffuse gas. The freefall time depends on how much mass is packed into a given volume. When density is high, gravity has less distance to pull material inward, and the inward acceleration becomes stronger. This simple relationship explains why small, dense cores can evolve much faster than the broader molecular cloud that surrounds them. Observed Class 0 lifetimes are sometimes compared to calculated freefall times to see whether collapse is regulated or nearly unimpeded. If Class 0 objects live much longer than a freefall time, that suggests additional support like magnetic fields or turbulences slowing the collapse. If lifetimes are closer to freefall estimates, gravity may be dominating more directly. These comparisons help researchers understand how much resistance collapsing gas really encounters. The final stellar mass depends strongly on how envelope material is divided between what reaches the star, what remains in the disk, and what is expelled in outflows. A core might begin with a certain amount of mass, but not all of it ends up in the star. Some material is ejected by jets and winds, and some may remain in the disk to form planets or be dispersed later. This partitioning means the star's birth mass reflects both initial conditions and feedback processes. Protostellar outflows can entrain surrounding cloud gas, sweeping it up and increasing the total mass seen in molecular outflow observations. The jet itself may be relatively light, but as it plows through the cloud, it pushes and drags additional material along. This makes the outflow appear massive and energetic. Measuring entrained mass helps estimate how strongly a young star is influencing its natal environment. Momentum injected by outflows can stir turbulence within star-forming regions, possibly slowing large-scale collapse. When multiple young stars launch jets, their combined effects can keep gas in motion. That motion adds internal support against gravity, at least temporarily. In this way, star formation can regulate itself, as newly formed stars inject energy back into the cloud. At the same time, outflows that clear channels through envelopes can reduce shielding and allow more radiation to penetrate. If ultraviolet or X-ray photons travel along outflow cavities, they can alter local chemistry and ionization levels. This changes how molecules form and how gas couples to magnetic fields. So outflows both remove mass and subtly reshape the physical conditions of the surrounding material. Protostellar disks are sites of rich chemical evolution, where temperature gradients, ultraviolet radiation, and X-rays drive reactions. The inner disk may be warm enough for complex reactions in the gas phase, while the outer disk remains cold and dominated by ice chemistry. These chemical zones are layered both radially and vertically. The disk becomes not just a feeding structure, but also a dynamic chemical laboratory. Complex organic molecules can form in warm inner envelopes and then be delivered into disks through inflow. As material spirals inward, it carries chemical signatures from earlier cloud phases. Once in the disk, these molecules can either remain in the gas or freeze onto grains depending on temperature. This transport connects early cloud chemistry with later planet-building environments. Ices in outer disk regions can preserve early cloud chemistry for long periods. At low temperatures, molecules remain frozen onto dust grains and are shielded from destructive radiation. These icy mantles can later become incorporated into comets or planetesimals. In this way, the chemical memory of the molecular cloud can survive into planetary systems. Disk winds can remove both mass and angular momentum from the disk surface. By lifting material away, winds can gradually thin the disk and shorten its lifetime. At the same time, by carrying away angular momentum, winds help gas in the disk move inward. This dual role makes disk winds important for understanding both how stars grow and how disks disperse. Magnetically driven disk winds are one proposed mechanism for this mass and angular momentum removal. In these models, magnetic field lines anchored in the disk act like rigid wires, flinging gas outward along curved paths. The process is somewhat analogous to a rotating sprinkler throwing water outward. Observations of certain line profiles and velocity structures support the presence of such winds in some young systems. Photoevaporative winds are driven by high-energy photons that heat the disk surface until gas becomes hot enough to escape the star's gravity. Ultraviolet and X-ray radiation can raise temperatures in the upper layers of the disk. When thermal energy exceeds gravitational binding energy at certain radii, gas flows away as a wind. Over time, this can open inner holes and contribute to disk clearing. Disk dispersal timescales vary from system to system, but many protoplanetary disks disappear within a few million years. This relatively short window sets a time limit for planet formation in gas-rich environments. If giant planets are to form, they must do so before most of the gas is gone. The timing of dispersal therefore shapes the architecture of planetary systems. Once a young star reaches the main sequence, sustained hydrogen fusion provides long-term stability. The outward pressure from fusion balances inward gravitational pull. This balance allows the star to shine steadily for millions or billions of years depending on its mass. Reaching this stage marks the end of the main assembly phase. The spectral classification of a main sequence star includes a luminosity class 5, indicating it is in the stable hydrogen-burning phase. This classification system organizes stars by temperature and size. The V designation helps distinguish mature main sequence stars from giants or supergiants. It reflects a star that has settled into equilibrium after its turbulent birth. The Sun's classification as G2V indicates both its surface temperature and its main sequence status. The G2 part refers to its temperature and spectral characteristics, while a V confirms stable hydrogen burning. This simple code summarizes much of what matters physically about the Sun. It also reminds us that our own star once passed through the same protostellar stages described earlier. The earliest embedded stages of star formation are best observed at far-infrared and millimeter wavelengths. Dust that blocks visible light becomes transparent at longer wavelengths. By observing in these bands, astronomers can peer into the cold interiors of clouds. This approach has revolutionized our understanding of hidden protostars. For infrared surveys can inventory protostars and measure their bolometric luminosities by capturing reprocessed dust emission. Space telescopes sensitive to these wavelengths have mapped entire molecular clouds. By detecting faint embedded objects, these surveys help estimate lifetimes and population statistics. They also reveal temperature variations across clouds. Catalogues combining data from multiple observatories allow classification of large samples of young stellar objects. By comparing colors and spectral energy distributions, astronomers assign evolutionary stages. These catalogues are essential for statistical studies of star formation. They also help identify unusual or rare objects for detailed follow-up. Bolometric temperature and infrared spectral indices are commonly used together to classify young stars. Each measure has strengths and weaknesses, so combining them improves reliability. For example, bolometric temperature captures overall energy distribution, while spectral slope highlights certain wavelength ranges. Together, they offer a clearer picture of evolutionary state. Dense core surveys help map core mass functions, which can be compared to the stellar initial mass function. If core masses and stellar masses are related, this suggests fragmentation sets part of the IMF. However, not all core mass becomes stellar mass. Comparing the two distributions provides insight into efficiency and mass loss. Quarter-star efficiency is less than 100% because outflows and feedback remove some material. Even if a core begins with a certain mass, only a fraction ends up in the star. This inefficiency helps explain why clouds are not fully converted into stars. It also influences how clusters evolve. Some theoretical work suggests filament fragmentation sets a characteristic spacing between cores. In idealized cylindrical models, gravity produces a preferred separation distance. This pattern is sometimes observed along filaments. However, real filaments are affected by turbulence and magnetic fields. The spacing of dense cores along filaments can reflect the fastest-growing unstable mode predicted by theory. If gravity dominates, regular patterns may appear. Observers compare measured spacings to theoretical expectations. Differences help refine models of fragmentation. In HEMUS regions, massive, dense cores around 0.1 parsec in size are considered possible progenitors of massive stars. These cores contain enough mass to form large stars or small groups. Their properties differ from typical low-mass cores. Studying them helps explain how the most luminous stars are born. Extraction algorithms applied to dust maps identify dense cores and estimate their masses and temperatures. These computational tools analyze emission patterns to isolate compact structures. By fitting models to dust emission, astronomers infer physical parameters. This method allows large statistical studies across entire clouds. The Aquila Rift is one region frequently used to study dense core populations. Surveys there have identified numerous prestellar and protostellar cores. Comparing bound and unbound cores helps determine which are likely to collapse. Such regions serve as laboratories for testing star formation theories. Core catalogues often show a subset of gravitationally bound cores and another subset of transient condensations. Bound cores are more likely to proceed toward collapse. Unbound ones may disperse if support remains strong. Distinguishing between them clarifies which structures truly seed stars. The fraction of bound cores increases with local column density, meaning denser environments favor collapse. Where gas is more concentrated, gravity has a stronger influence. This supports the idea of a threshold for efficient star formation. Dense gas is the most reliable predictor of star birth. A column density threshold is sometimes proposed as the point above which core formation becomes efficient. Below that threshold, gas may remain diffuse and stable. Above it, fragmentation into cores accelerates. This concept links large-scale cloud structure to small-scale star formation. Filament formation can occur widely in cold interstellar gas, but only the densest segments become star-forming. Many filaments never produce stars. Only when mass per unit length exceeds critical values does gravitational instability occur. This explains why star formation is patchy rather than uniform. Filament networks appear in many molecular clouds, even those forming few stars. Their ubiquity suggests that turbulence and large-scale flows naturally create them. However, their presence alone does not guarantee collapse. Conditions within each filament determine its fate. The presence of filaments does not automatically mean star formation will follow. A filament must accumulate enough mass and reach sufficient density. External pressure and magnetic support can stabilize otherwise dense-looking structures. Only when gravity overcomes these factors does fragmentation proceed. A filament's critical lying mass determines whether it is unstable to radial collapse. If the mass per unit length exceeds this value, gravity can cause contraction and fragmentation. Below it, thermal pressure may maintain stability. This threshold depends on temperature and other factors. External pressure and magnetic fields modify the simple critical line mass picture. In realistic environments, filaments are not isolated cylinders. Surrounding gas and magnetic forces can either assist or resist collapse. Accounting for these influences is essential for accurate modeling. Observations show that many star-forming cores lie within filaments that appear supercritical. This supports theoretical predictions about line mass thresholds. However, measurements of magnetic fields and turbulence are also necessary to confirm instability. Observational agreement strengthens confidence in the filamentary model. Some star formation occurs in relative isolation, within small globules rather than giant clusters. These environments allow study of collapse without strong external disturbances. The physics may be similar, but the context is simpler. Isolated systems highlight the universality of core collapse processes. Isolated star formation provides clearer examples of disk and outflow development. Without nearby massive stars, radiation feedback is weaker. This makes it easier to disentangle internal processes from external influences. Such systems are valuable benchmarks for theory. Even in isolation, angular momentum conservation still produces disks and outflows. These features are fundamental outcomes of rotating collapse. They do not require crowded environments. Their presence across many contexts confirms the robustness of disk-mediated star formation. Protostellar envelopes can show infold signatures while simultaneously driving bipolar outflows. This demonstrates that inward and outward motions coexist. Material can be accreting toward the center even as other gas is expelled. Star formation is therefore a dynamic exchange rather than a one-way flow. Outflow cavities can channel radiation, making protostars appear brighter in certain directions. If we look down a cavity, we may see deeper into the system. If we view from the side, the envelope may obscure the central region. Geometry therefore influences classification and luminosity estimates. Young stars can drive collimated jets for much of their pre-main sequence evolution. Jets are not confined only to the very earliest moments. Continued accretion supports ongoing launching. Their persistence shows that angular momentum removal remains important throughout early evolution. The chemistry in shocks along jets can differ dramatically from calm cloud gas. High temperatures activate reactions that are otherwise inefficient. Molecules can be destroyed and reformed in new combinations. Shock chemistry thus produces distinctive spectral fingerprints. Molecular bow shocks are infrared counterparts to optical HH objects. They trace regions where jets impact molecular gas at supersonic speeds. These bow-shaped features mark the leading edges of interaction. Observing them helps measure shock strength and ambient density. Some hulated outflows span multiple parsecs, indicating prolonged activity. Such scale implies sustained accretion and ejection over long periods. Large-scale flows can significantly reshape their parent clouds. Their size highlights the far-reaching influence of forming stars. Observations of HH systems in Orion have been central to understanding outflows. Orion's relative proximity allows detailed study. Tracking motions and spectra in Orion has clarified jet speeds and structures. These insights apply to other star-forming regions as well. Bok globules are small, dense, dark pockets of molecular gas and dust that can host star formation in a relatively compact setting. They appear as inky silhouettes against brighter background star fields because their dust box visible light. Even though they are much smaller than giant molecular clouds, they can still contain enough cold material for gravity to begin pulling inward. Studying them is useful because the environment is simpler and often less crowded than large star-forming complexes. Barnard 68 is one of the most famous Bok globules because it forms a remarkably clear, rounded, dark patch that stands out against a dense field of background stars. Its shape and contrast make it an excellent target for measuring how dust absorbs light at different wavelengths. By analyzing how it dims starlight, astronomers infer properties like column density and internal structure. It's a clear example of how a star-forming object can be seen by what it hides rather than what it emits. Barnard 68 is also relatively nearby on galactic terms, which matters because distance strongly affects how much detail we can resolve. When an object is closer, telescopes can map finer structure and detect fainter features. This makes it easier to test models of dense core stability, temperature gradients, and chemistry. Nearby globules become natural laboratories for the early conditions that can lead to collapse. The interior of a dark globule can be extremely cold compared with the more diffuse interstellar medium, and that coldness helps explain why it remains compact rather than dispersing quickly. With less thermal energy, gas particles move more slowly, reducing internal pressure that would otherwise push outward. Cold conditions also encourage molecules and ices to persist on dust grains, changing chemistry and cooling. In simple terms, the chill inside the globule makes it easier for gravity to hold the structure together. A globule's mass and temperature together help determine whether it is stable or likely to collapse into one or more stars. If it has enough mass packed into a small enough volume, gravity can dominate. If it is too warm or too light, pressure support can keep it from collapsing, at least for a time. This stability question is often framed as a balance of inward pull versus outward support, with small changes in conditions sometimes tipping the outcome. Binary star dynamics provide one of the most direct ways astronomers measure stellar masses, because orbital motion responds to gravity in a straightforward way. When two stars orbit each other, their speeds and separations reveal the total mass of the system through well-tested gravitational relationships. With additional information, astronomers can separate that total into individual masses. These mass measurements are essential because mass controls nearly everything about a star's evolution and lifetime. Unresolved binaries can bias estimates of the initial mass function because two stars' light can blend together and look like one brighter, more massive star. If surveys cannot distinguish the pair, the system's combined brightness may be interpreted as a single object. That can shift inferred mass distributions and skew statistics about how many stars form at different masses. Correcting for this requires careful modeling, high-resolution imaging, and long-term monitoring. Some models of massive star formation emphasize competitive accretion, where many forming stars share a common gas reservoir in a cluster environment. In this view, seeds that end up near dense central regions can draw in more material, growing faster and becoming more massive. The process is influenced by gravity, gas flows, and the changing potential of the forming cluster. It's a way of explaining why the most massive stars often appear in the densest parts of stellar nurseries. Another proposed route for producing very massive objects is mergers, or coalescence, in extremely dense young clusters. If stellar densities become high enough, close encounters and interactions can lead to collisions or the merging of protostars. This is not thought to be the dominant path everywhere, but it is discussed as a possibility in the most extreme environments. It highlights how dynamic star-star interactions can sometimes compete with pure gas accretion in shaping the high-mass end. Radiation pressure is a major challenge for massive star formation because bright, growing protostars can push outward strongly on dust mixed with the inflowing gas. Photons carry momentum, and when dust absorbs or scatters those photons, it feels a push. In a spherically symmetric picture, this push could oppose or even halt inflow. Understanding how massive stars keep growing requires explaining how accretion can persist despite this intense radiative feedback. One proposed solution is non-spherical accretion through disks along with the flashlight effect, where radiation escapes more easily in some directions than others. If outflow cavities and lower density polar regions let photons stream outward, the midplane can remain comparatively shielded. Gas can then continue flowing in through the denser, flattened disk. This geometry-based pathway shows how shape and directionality can matter as much as raw luminosity in controlling accretion. In HEMA star formation, ionization can also influence inflow because ionized gas is hot and pressurized, tending to expand outward. As a massive protostar emits stronger ultraviolet radiation, it creates an H2 region that can push on nearby material. Whether this shuts off accretion depends on density, gravity, and the presence of focused inflow streams. In many realistic scenarios, accretion can continue for a time even as ionized regions develop, but the interaction is complex. Ultra-compact H2 regions are small, dense ionized zones around very young massive stars that remain embedded in their natal material. They are compact because surrounding dense gas and ongoing inflow can confine the ionized plasma. They are important observational markers of early massive star evolution, often detected via radio emission. These regions sit at the boundary between continued growth and feedback strong enough to reshape the environment. The lifetimes and expansion behavior of H2 regions depend strongly on the density structure around them and on turbulent conditions in the parent cloud. In a dense medium, expansion can be slowed or channeled, while in lower density directions, ionized gas may break out more easily. Turbulence creates clumps and cavities that make the boundary irregular rather than smooth. This is why real H2 regions often look asymmetric and structured instead of like neat, expanding spheres. Massive stars tend to form in clustered environments where gas surface densities and pressures are high, providing the raw conditions needed for sustained high accretion rates. Dense environments can deliver more material faster, which is essential because massive stars must grow quickly before feedback becomes overwhelming. Clustering also changes dynamics, because gravitational interactions and shared gas potentials shape how material flows. The presence of many forming stars nearby is therefore a common feature, not an exception, in HEMAS nurseries. HEMAS protostars can show evidence for episodic accretion as well, which is important because it tests whether bursty growth is universal across mass ranges. In massive systems, bursts can produce strong infrared brightening and rapid changes in surrounding dust heating. Because massive stars affect their environment so strongly, bursts may also have larger-scale consequences for ionization and chemistry. Observing and modeling these bursts helps connect variability to the assembly of the most luminous stars. Accretion bursts in massive systems are often studied through infrared variability and spectral diagnostics that probe hot inner disk regions. When accretion increases, the inner disk heats up and radiates more strongly in the infrared. Spectral lines can broaden or change shape, reflecting hotter gas and different kinematics. These tools allow astronomers to infer changes in accretion even when the central regions remain heavily obscured by dust. Protostellar radiative transfer effects can cause the same object to look very different depending on viewing angle, especially when outflow cavities carve low-density paths. If we look along a cavity, we may see warmer inner regions and classify the object as more evolved. If we look through the thick envelope, the spectrum may shift to longer wavelengths and suggest a younger stage. This angle dependence is one reason classification has uncertainty. Observations capture appearance, and appearance depends on geometry. Flat-spectrum young stellar objects are sometimes interpreted as intermediate cases between Class 1 and Class 2, or as systems where geometry strongly affects the observed spectral slope. A spectrum can look flat if contributions from disk and envelope combine in a particular way, or if we see a partially cleared path through dust. Flat spectrum sources remind us that evolution is not always cleanly separated into neat categories. They represent either genuine transitional states or viewing angle variations that blur boundaries. Measuring protostellar masses directly is difficult because envelopes and disks obscure the stellar photosphere and complicate dynamical interpretation. In many cases, the star itself cannot be seen clearly, and the motion of surrounding gas includes inflow, rotation, and outflow all at once. This makes it hard to isolate the gravitational signature of the star alone. As a result, protostellar masses are often estimated indirectly, with uncertainties tied to models and assumptions. The very first stars, often called population the third, formed in metal-free gas, made almost entirely of hydrogen and helium, with essentially no dust. Without metals, the cooling pathways were limited compared with present-day clouds. This difference changes how gas fragments and what typical initial masses might be. Studying population, the third star formation, is central to understanding how the earliest luminous objects shaped the universe's evolution. Simulations commonly place first star formation in small dark matter mini-halos, where gravity pulls primordial gas into dense central regions. Dark matter provides the gravitational well that collects the gas, even though dark matter does not cool or radiate like normal matter. As gas accumulates, it can form molecular hydrogen and radiate away heat, allowing further collapse. These mini-halos act as the earliest cradles where star formation becomes possible. Population, the third formation, is often discussed at high redshifts around 2030, meaning it occurred very early in cosmic history. At those times, the universe was much denser than it is today, and structure formation was just beginning. The conditions for gas cooling, collapse, and feedback were therefore very different from the present Milky Way. This early timing connects first stars directly to the dawn of galaxies. Without metals and dust, primordial gas relied heavily on molecular hydrogen, H2, as the main coolant that could lower temperatures enough for collapse. H2 is less efficient at cooling than many metal-based lines, which tends to keep gas warmer during contraction. Warmer gas resists fragmentation into many small pieces, pushing typical collapse scales upward. That difference is a key reason early star formation is often expected to favor larger characteristic masses. Three-body reactions become important at high densities in primordial gas, efficiently forming H2 and boosting cooling at late stages of collapse. In these reactions, two hydrogen atoms can form H2 when a third particle carries away excess energy, something that becomes more likely when densities are high. The newly formed H2 then radiates energy through its molecular transitions, helping the gas cool further. This density-dependent chemistry is one of the distinctive features of metal-free star formation physics. Reduced cooling in metal-free gas tends to produce larger fragmentation scales, often leading to more massive protostellar objects than typical star formation today. When gas stays warmer, the gene's mass increases, meaning larger chunks are gravitationally unstable rather than many small ones. This tends to concentrate mass into fewer forming centers. The outcome, in many models, is that the earliest stars could be very massive compared with the common low-mass stars we see forming now. Population-deferred stars are expected to have been extremely luminous and short-lived compared with low-mass stars, because higher mass drives faster fuel consumption. A massive star burns through its nuclear fuel quickly and ends its life in violent ways that disperse heavy elements. Even though these stars may have been rare, their radiation and explosions could dominate their local environments. Their brief lives had outsized influence on early chemical enrichment. The first stars helped initiate reionization-era feedback by producing ultraviolet photons that affected surrounding intergalactic gas. Before reionization, much of the universe's hydrogen was neutral. Early luminous sources began ionizing it. Ionization heats gas and changes how it collapses into later structures, affecting future galaxy formation. Thus, star birth in the early universe was tied directly to large-scale changes in the state of cosmic gas. Chemical enrichment from the first supernova introduced metals, enabling more efficient cooling and changing subsequent star formation modes. Metals provide additional line emission cooling pathways and support dust production. With better cooling, gas can fragment more easily into smaller masses, allowing the formation of longer-lived low-mass stars. This transition from pristine to enriched star formation is a turning point in cosmic history. In present-day star formation, dust cooling can become important at high densities, aiding fragmentation into low-mass cores. At sufficiently high density, gas and dust exchange heat effectively, and dust can radiate energy away. This helps keep collapsing regions from overheating and supports the formation of smaller fragments. Dust therefore influences not only opacity and chemistry, but also the thermal physics that shapes what masses form. Metal line cooling from elements like carbon and oxygen can lower gas temperatures in enriched environments, especially at relatively low densities where dust cooling is less dominant. These elements emit in finesse structure lines that can carry energy away efficiently. Lower temperatures favor fragmentation into smaller, gravitationally unstable pieces. This is part of why metallicity is often linked to characteristic stellar masses across different environments. The thermal pressure inside an H2 region is typically much higher than in surrounding cold molecular gas, because ionized gas is much hotter. Higher temperature means higher particle speeds, which increases pressure. This pressure difference drives expansion and helps carve cavities and shells. In a star-forming region, the pressure contrast between ionized and molecular gas is one of the strongest drivers of reshaping. The expansion speed of an ionization front depends on density gradients and on the ionizing photon output of the central stars. In denser material, The front advances more slowly because recombinations are more frequent and because there is more mass to push. In lower density directions, it can move faster and break out, creating asymmetric expansion. This is why many H2 regions show blister shapes or directional flows instead of uniform growth. Dense filaments feeding a forming massive star can continue delivering material even as ionizing radiation grows, depending on geometry and confinement. If inflow is concentrated into narrow streams or shielded by dense gas, radiation may not immediately stop it. Gravity can also help hold ionized material near the star, complicating the simple picture of ionization pushing everything away. This interplay allows accretion to persist longer than a purely spherical model might suggest. In radiation magnetohydrodynamic simulations, ionizing feedback can eventually shut off accretion by disrupting inflowing filaments in some scenarios. As feedback grows, it can erode, heat, and redirect the gas flows that were feeding the star. Magnetic fields and turbulence alter exactly how this disruption unfolds, sometimes delaying it, sometimes accelerating it. These simulations are crucial because they combine multiple physical effects that operate together in real regions. Massive star feedback can create champagne flows, where ionized gas streams rapidly into lower density surroundings after breaking out of a denser region. The pressure gradient becomes steep, and ionized plasma flows away like gas rushing from an opened bottle. This can produce strong asymmetric structures and large-scale motion in the ionized region. Champagne flows are one-way feedback channels energy and mass into the broader interstellar medium. Compression by expanding shells can create regularly spaced condensations if the swept-up layer becomes gravitationally unstable. As material accumulates in a shell, it can cool and gain mass until gravity begins to fragment it. In idealized cases, the instability can produce a pattern of clumps along the shell. These clumps can become new dense cores, potentially forming a new generation of stars around the bubble. Triggered star formation can produce young objects at the periphery of H2 regions, sometimes appearing in arcs or rings around cavities. The basic idea is that expansion reshapes gas into dense edges, where collapse becomes easier. Observations sometimes show concentrations of young sources along these edges. However, interpreting such patterns requires care, because geometry and pre-existing structure can create similar-looking arrangements. Not every apparent ring of young stars indicates triggering, because projection effects and earlier cloud structure can mimic a ring. A three-dimensional cloud can look like a circle in a two-dimensional image if we view it from certain angles. Also, stars can form along pre-existing filaments that happen to lie around a cavity. This is why researchers avoid relying on appearance alone when deciding whether a region was triggered. Distinguishing triggering typically requires kinematic evidence and age gradients consistent with causal expansion and collapse. Scientists look for gas motions that match an expanding shell and for younger stars near the compressed edge compared with older stars closer in. They also compare timescales. Did the shell have time to form and fragment before the young stars appeared? When these pieces align, the triggering case becomes much stronger. The Carina Nebula contains active star formation under intense feedback from massive stars, making it a vivid place to study how radiation and winds sculpt clouds. In such regions, dense clumps and pillars survive within a much harsher environment than quiet nearby clouds. The contrast between eroded cavities and dense ridges shows how unevenly feedback acts. Carina illustrates how massive stars can both clear space and leave behind concentrated structures where new stars may still form. Infrared imaging can reveal protostars hidden behind thick dust that blocks visible light, effectively opening a window into the earliest embedded stages. In visible wavelengths, dust can make an active star-forming region look almost empty. In infrared, the same region can be crowded with newborn objects and worn dust structures. This is one reason modern star formation studies rely heavily on infrared surveys. JWST near-infrared imaging has highlighted fine structure in star-forming edges, including cavities and ridges where dense gas remains. Near-infrared sensitivity and resolution allow astronomers to see through dust better than visible light, while still capturing fine detail. This reveals how sharply some boundaries are carved and how intricate the surviving dense structures can be. Such images help connect feedback-driven shapes to underlying physical processes. Bright ionized rims can compress adjacent molecular gas, increasing pressure on the neutral side and potentially encouraging local collapse. When a ionization front meets dense material, it creates a glowing boundary and a pressure difference across it. The neutral gas may be squeezed, raising its density. Whether that compression actually triggers new stars depends on how strong and sustained it is compared with internal support. The edges of feedback-carved cavities can reveal young stellar objects and jets that were previously hidden by dust and line-of-sight confusion. As material is cleared, embedded sources become easier to detect at shorter wavelengths. Outflows that once ran into dense surrounding gas can become more visible as cavities open. This observational uncovering can make regions look like new stars suddenly appeared, when in fact they were simply revealed. Photoevaporation refers to gas being heated by radiation until it escapes as a wind, which can erode disks, globules, and cloud surfaces. High-energy photons raise the temperature of exposed gas layers, giving particles enough speed to flow away from the gravitational pull holding them. Over time, this mass loss reshapes structures and reduces available fuel. Photoevaporation is one of the most direct ways radiation feedback removes material from star-forming environments. Evaporating gaseous globules, or EG, are dense clumps being eroded by radiation, sometimes containing forming stars within them. The outer layers are heated and stripped away, while the denser interior survives longer. If a protostar is inside, the egg can act like a temporary protective shell. Eggs show how feedback can both destroy and momentarily preserve star-forming material, depending on density and timing. In massive regions, pillars often point toward ionizing sources because radiation preferentially removes less dense gas and leaves denser structures behind along the direction of illumination. The pillar's head is usually the densest part, resisting erosion longer. Over time, the shape records the direction of the dominant radiation field. This alignment helps astronomers infer which stars are driving the sculpting of the cloud. Dense cores can survive longer against evaporation due to higher self-shielding and gravitational binding. When density is high, radiation cannot penetrate as deeply, and the interior stays cooler and more protected. Gravity also helps hold material together, even as outer layers are stripped. This is why some small, bent structures remain embedded in harsh environments long after surrounding diffuse gas has been cleared. Observations of bright-rimmed clouds are used to study the interplay of ionization fronts and potential triggered collapse, because these clouds sit right at the boundary between ionized and molecular gas. Researchers map the rim's ionized emission and the molecular gas behind it to see how pressure and density change across the interface. They search for young objects and dense cores that might have formed in compressed layers. Bright rims provide a natural setting to test how external radiation can influence the earliest steps toward star formation. Star formation efficiency in a cloud is often low, meaning that a large portion of the cloud's mass never becomes part of a star. A cloud can contain enormous amounts of gas and dust, yet only a small fraction reaches the high densities needed to collapse. Much of the material may remain too diffuse, or it may be dispersed by feedback before it can join a collapsing core. This is one reason star-forming regions can look vast and heavy, while producing a comparatively modest amount of starlight. Feedback-driven cloud dispersal can set an upper limit on how many generations of stars a single cloud complex can make. As young stars turn on, they inject energy through jets, winds, and radiation, and massive stars can add strong ionization and later supernova shocks. These processes can heat and push gas outward, breaking the cloud apart or thinning it until collapse becomes difficult. Over time, the cloud's ability to keep forming stars fades as its densest structures are eroded or scattered. In giant molecular clouds, star formation is often localized to specific dense subregions rather than occurring evenly throughout the whole cloud. Some pockets become especially compressed, shielded, and gravitationally unstable, while neighboring areas remain relatively quiet. This unevenness comes from the cloud's internal structure filaments, hubs, and turbulent density variations. It means that star birth is often concentrated in hotspots of dense gas within a much larger, calmer reservoir. The same cloud can host both quiet Loma star formation and intense massive star formation, depending on local density and pressure. In calmer corners, small prestellar cores may form and collapse slowly into sun-like stars. In denser, more pressurized sections, gas can gather rapidly, feeding clusters and enabling the growth of massive protostars. This mix can exist side by side, showing that one cloud can contain multiple modes of star birth at once. As the observational appearance of a protostar depends strongly on wavelength, because dust blocks and reshapes light in different ways. In visible light, a deeply embedded protostar might be completely hidden, making the region seem empty. In infrared, the same object can appear bright because worn dust re-emits energy at longer wavelengths. In millimeter light, cold dust and gas become even more visible, revealing the mass and structure of envelopes and disks. Because of that strong wavelength dependence, multi-wavelength surveys are essential for building a complete census of embedded populations. No single band can capture every stage with equal clarity. Infrared finds warm dust and embedded sources, millimeter maps cold material and disks, and optical reveals the more exposed young stars. Combining these views helps prevent missing entire categories of objects simply because they are hidden in one wavelength range. Young star catalogues often require careful cleaning for contaminants, such as background galaxies that can mimic the colors of embedded objects. At faint levels, distant galaxies can appear as red infrared sources, and without extra checks they can be mistaken for protostars. Astronomers reduce this confusion by using multiple color criteria, spatial clustering, and cross-matching with other wavelengths. This careful filtering matters because even a small fraction of contaminants can distort statistics about lifetimes and star formation rates. Because dust reddening changes colors, classification methods must account for extinction along the line of sight. Dust absorbs and scatters shorter wavelengths more strongly, making objects look redder and dimmer than they truly are. If extinction isn't properly considered, a more evolved source can be mistaken for a younger embedded one, or the reverse. Correcting for extinction makes comparisons fairer and helps evolutionary indicators track real physical differences rather than just intervening dust. Holometric luminosity is especially useful because it estimates the total energy output across all wavelengths, not just what is seen in a single band. This is important for protostars whose light is heavily reprocessed by dust, shifting energy into infrared and millimeter wavelengths. By integrating across the spectrum, astronomers get a more complete picture of how much power the system is producing. That makes bolometric luminosity a better bridge between observation and the physical processes of accretion and contraction. Large young stellar object surveys show that even within one region, sources span a wide range of luminosities and inferred accretion rates. This variety suggests that star growth is not a single steady pace for everyone. Some objects may be in quiet phases, while others are actively accreting or experiencing recent bursts. The wide spread supports the idea that time variability and environmental differences are normal features of star formation. After accretion wanes, contraction toward the main sequence continues as the young star radiates away leftover heat from its formation. Even when most of the mass is already assembled, the star is still settling internally. It slowly shrinks, its interior pressures and temperatures adjust, and it approaches the stable structure of long-term hydrogen burning. This phase is quieter than the embedded stage, but it is still a meaningful part of becoming a mature star. The pre-main sequence contraction time depends strongly on stellar mass, with lower mass stars taking longer to reach the main sequence. Smaller stars radiate energy more slowly relative to their mass, so they spend more time contracting and adjusting before stable hydrogen fusion dominates. Higher mass stars evolve faster, crossing the pre-main sequence stage quickly by comparison. This mass dependence is one reason star-forming regions can contain a mix of objects at different evolutionary stages at the same time. Once stable hydrogen burning begins, the star reaches a long-lived equilibrium in which outward pressure from fusion balances inward gravity. This balance is what allows a star to shine steadily for a large fraction of its lifetime. The core becomes a controlled energy source, rather than relying mainly on gravitational contraction. In a calm, physical sense, the star has found its steady working state. The birth environment can leave lasting signatures, including how fast a star rotates. During early stages, interactions between the star and its disk can regulate rotation, and later, winds and magnetic braking can remove angular momentum. Stars born with different disk lifetimes or different magnetic coupling histories can end up spinning at different rates. This means rotation can carry a quiet record of how a star's earliest environment behaved. Early stellar winds can remove additional angular momentum after disk dispersal, shaping how rotation evolves through youth. Even once the disk fades, a magnetized wind can carry away angular momentum from the star's outer layers. Over time, this wind-driven braking can slow the star, changing activity levels and magnetic behavior. The result is a gradual transition from the highly active youth of the star toward a more settled, slower-spinning adulthood. Stars formed in clusters can later drift apart due to internal motions and the tidal influence of the galaxy. The cluster's birth velocities and gravitational interactions gently spread members outward over time. Encounters and the gradual loss of remaining gas can also loosen the cluster's gravitational grip. Eventually, many stars that were once neighbors become part of the broader galactic field. Some of the Sun's sibling stars are expected to have dispersed throughout the Milky Way over billions of years. The Sun likely formed in a group rather than alone, but that birth group did not remain intact as a tight cluster forever. Galactic rotation, gravitational encounters, and long-term tides slowly separated the members. This idea connects our own star to the general story of clustered star formation and later dispersal. The stellar initial mass function, combined with a galaxy's star formation history, determines how many long-lived low-mass stars versus short-lived massive stars exist at any moment. Low-mass stars accumulate because they live so long, while massive stars come and go quickly. The balance affects a galaxy's light, chemical evolution, and feedback strength. In that way, the mass distribution at birth shapes the character of entire galaxies. Because massive stars die quickly, ongoing star formation is needed to maintain populations of bright O and B stars in spiral arms. These luminous stars do not last long on cosmic timescales, so their presence signals recent star formation. This is why spiral arms often appear bright and blue in galaxies. They highlight places where stars have formed relatively recently. Without continued formation, that bright Hay-mass population would fade rapidly. The continuous cycling of gas into stars and back into the interstellar medium through winds and supernova is central to galactic chemical evolution. Stars lock up gas while they live, then return material sometimes enriched with newly formed elements when they lose mass or explode. This recycling changes the composition of the gas that future stars will form from. Over time, it builds the chemical variety needed for complex molecules, rocky planets, and many of the conditions we associate with later cosmic richness. The first stars began this chemical cycle in the universe by producing the earliest heavy elements and dispersing them into their surroundings. Before them, the universe had essentially only hydrogen, helium, and traces of lithium. Their lives and deaths created and spread heavier elements for the first time. This made later star formation fundamentally different from the initial pristine era. Metal enrichment enables more efficient cooling and dust formation, which helps later clouds fragment into smaller pieces and form lower mass stars. Metals provide additional radiative cooling channels, and dust helps both cooling and shielding. With stronger cooling, gas can break into many smaller collapsing regions, instead of remaining warm and clumped into a few large ones. This is one reason later generations of stars include many long-lived low-mass stars. Some theoretical work suggests population, the third star formation may have persisted longer in pockets of pristine gas than once assumed, depending on mixing and feedback. Even if many regions became enriched, some locations might have avoided rapid mixing of metals. In such pockets, primordial-like conditions could last longer, allowing rare continued formation of metal-free stars. This idea highlights how uneven chemical enrichment can be across space and time. Even today, understanding how metallicity changes fragmentation is important for interpreting star formation in low-metallicity dwarf galaxies. These galaxies can have lower dust content and different cooling behavior than the Milky Way. That can influence cloud temperatures, fragmentation scales, and perhaps the typical masses of stars formed. Studying them helps connect nearby star formation to earlier cosmic conditions. Observations across different environments help test whether key processes like disk evolution, accretion variability, and the EAMF are universal or environment-dependent. If the same patterns appear in many settings, that argues for robust underlying physics. If strong differences appear, it suggests the environment can reshape outcomes in meaningful ways. This kind of comparison is essential for building star formation theories that work beyond a single neighborhood. High-resolution facilities, including infrared space telescopes and millimeter interferometers, continue to reveal substructures in disks and embedded cores. These details rings, gaps, filaments, compact cores give direct constraints on models that were once mostly theoretical. Better resolution also reduces confusion in crowded regions, separating multiple sources that would otherwise blend together. As observations sharpen, theories must become more precise to match them. The combination of filamentary cloud structure, core fragmentation, disk accretion, and jet/outflow feedback provides a coherent, multiscale picture of how stars gain mass. Large-scale flows gather material into filaments. Filaments fragment into cores. Cores collapse into protostars, and disks regulate how mass reaches the star. Meanwhile, outflows return momentum and energy to the environment, shaping what happens next. The overall process is a connected chain rather than isolated steps. At each scale, there are competing influences: gravity versus pressure, turbulence, magnetic fields, and radiation that can tilt outcomes in different directions. In one location, turbulence may dominate and delay collapse. In another, gravity may quickly gather material. Magnetic fields can guide flows or slow rotation, while radiation can erode or compress gas depending on geometry. This competition is why star formation produces both consistent patterns and wide variety. Many uncertainties in star formation relate to time variability, how accretion changes when feedback turns on, and how quickly environments disperse. A protostar may look faint for long intervals and then brighten during a burst, while outflows can vary in strength and direction. Massive stars can rapidly change the environment once their ionizing radiation grows strong. Capturing these time-dependent behaviors is crucial for translating snapshot observations into true evolutionary stories. In a forming cluster, rapid gas removal by feedback can unbind the cluster if the gravitational potential drops too quickly. Early clusters often still contain substantial gas mass, and if that gas is expelled suddenly, the remaining stars may no longer be held tightly together. They can drift apart and become part of the galactic field. This is one pathway by which many stars born together end up widely separated later. If gas is removed more gently, or if the star formation efficiency is high enough, a bound open cluster can remain after formation. Slow removal gives the stellar system time to adjust and revirialize. With enough stellar mass left behind, gravity can keep the group intact. This difference in gas removal timing helps explain why some birth environments leave behind long-lived clusters, while others dissolve. Very dense early clusters can experience strong dynamical evolution, changing binary fractions and ejecting some members. Close encounters can tighten some binaries, disrupt others, and fling stars outward of higher speeds. Over time, these interactions reshape the cluster's internal structure and membership. This dynamical processing means the properties of stars and systems we observe later may differ from their initial birth configuration. Massive stars can photoionize and disperse surrounding gas on timescales comparable to or shorter than low-mass star formation timescales in the same region. That means low-mass protostars can still be assembling while massive neighbors are already transforming the shared environment. Ionization fronts, winds, and radiation pressure can remove fuel and change local pressures. This is one reason massive star feedback is often considered a dominant regulator in clustered regions. The most massive stars can therefore regulate the environment that lower-mass protostars are still accreting from. They can carve cavities, reduce shielding, and disrupt inflowing filaments. But they can also compress gas in certain zones and encourage collapse there. The net outcome depends on geometry, timing, and density structure. This interplay is one of the reasons star-forming regions can show both suppression and triggering in neighboring areas. Some galaxies show suppressed star formation associated with energetic central activity, while in other cases, shocks and jets can compress gas and induce star formation. Energetic processes can heat gas or drive turbulence that prevents collapse, yet in some conditions, the same energy can compress gas into dense, star-forming layers. Whether star formation is quenched or enhanced depends on how energy couples to the interstellar medium. This illustrates that feedback can have multiple outcomes across galactic environments. Galaxy-scale star formation is often discussed in terms of relations between gas surface density and star formation rate. The basic idea is that regions with more gas per unit, area specially more dense, gas tend to form stars more rapidly. These relations help connect local cloud physics to whole galaxy behavior. They also provide a way to compare very different galaxies using common measurable quantities. On cosmic timescales, the star formation history of the universe peaked at intermediate redshifts and declined toward today. This reflects changes in gas supply, galaxy mergers, feedback strength, and the overall pace of structure growth. When the universe had more cold gas available in galaxies, star formation could be more intense. As gas supplies diminished or became harder to cool, the cosmic average star formation rate dropped. The IMF is a key ingredient in converting observed light into inferred star formation rates because it determines how many luminous massive stars are present per unit total stellar mass formed. Massive stars dominate ultraviolet emission, even though they represent a small fraction of the mass. If the IMF shape changes, the same observed light could correspond to different total mass formation. This is why IMF assumptions matter so much for interpreting galaxy observations. Because massive stars are rare but dominate ultraviolet output, small changes in the Haymass IMF slope can strongly affect inferred star formation properties. A slightly top-heavier IMF would produce more UV light per unit mass, while a slightly steeper IMF would produce less. This sensitivity means uncertainties in the IMF propagate into uncertainties in star formation rates, feedback estimates, and chemical enrichment predictions. It is a quiet but powerful lever in astrophysical interpretation. The earliest phases of star formation are sometimes described as Class 1 or starless core phases in classification schemes that extend before Class 0. In this stage, a dense core exists but has not yet formed a central protostar. Observations focus on cold dust emission and dense gas tracers to identify cores likely to collapse. This phase matters because it captures the conditions that set up the later protostellar evolution. Protostellar evolution includes a stage where the object contracts and heats until conditions allow sustained hydrogen fusion in the core. Early on, energy comes mainly from accretion and contraction. As density and temperature rise, the interior moves toward the threshold for long-term fusion. This transition marks the shift from a forming object powered mainly by gravity to a stable star powered by nuclear reactions. For low-mass stars, the time from initial collapse to main sequence arrival is much longer than for HEMAS stars. Low-mass objects contract more slowly and can spend extended periods as pre-main sequence stars. High-mass stars, by contrast, can become hot enough for hydrogen burning relatively quickly. This mass dependence affects how mixed a young region looks, with different masses reaching different milestones at different times. High-mass stars can begin hydrogen burning while still accreting significantly, unlike many low-mass stars that finish most of their accretion earlier. This means a massive star can be both alive as a fusion-powered star and still in an active growth phase. It complicates the idea of a clean separation between formation and main sequence life. It also strengthens feedback early, because a burning massive star produces strong radiation while accretion is ongoing. In many models, fragmentation sets the initial number of forming seeds, while later accretion and dynamical interactions redistribute mass among them. Early fragmentation determines how many cores and protostars appear. After that, competition for gas, disk processes, and encounters in clusters can shift which objects gain more mass. This layered approach helps explain why star formation outcomes depend on both initial cloud structure and later environmental dynamics. Competitive accretion frameworks emphasize that stars in denser central regions of a forming cluster can accrete more, biasing HEMAS formation toward cluster centers. Gas flows tend to converge in deeper gravitational potentials, delivering more material there. Protostars located in these hubs can grow faster and become more massive. This idea connects cluster-scale gravity to the emergence of the most massive members. Coalescence scenarios for massive stars require exceptionally high stellar densities and short encounter timescales. For mergers to be common, protostars must pass very close to one another frequently. That condition is rare and likely limited to extreme environments. Even when mergers are not dominant, considering them highlights how cluster density can influence the pathways available for building very massive objects. Observational evidence for massive star formation via disks includes rotating structures and outflows aligned with rotation axes in many regions. Disk-like kinematics and bipolar flows suggest that, as in low-mass formation, a flattened accretion structure can feed the growing star. Outflows provide indirect support because they often trace disk-anchored launching processes. These observations strengthen the case that disk-mediated accretion is important across the mass spectrum. HEMAS protostellar accretion bursts may be detectable through infrared outbursts and maser variability in some systems. A burst can rapidly heat surrounding dust, increasing infrared emission, while changing shock conditions can alter maser brightness. Monitoring these signals gives a way to study growth episodes in obscured massive systems. It also suggests that variability may be a common feature, not an exception, even in HEMAS star birth. Protostellar jets can precess if the source is in a binary system or if the disk orientation changes over time. Precession causes the jet direction to slowly sweep out a cone, producing curved or S-shaped outflow patterns. This can reveal hidden companions or torque processes acting on the disk. Jet shapes can therefore carry information about the system's dynamical structure that is otherwise difficult to measure. Some HH systems show that outflows can persist through significant portions of early stellar evolution, not only at the instant of first collapse. The continued presence of jets indicates continued accretion and the ongoing need to remove angular momentum. Over time, the outflow can carve cavities, stir the local cloud, and change observational appearance. Persistent outflows are one of the ways forming stars steadily interact with their environments. Despite the complexity, a consistent observational theme is that star birth is concentrated in dense, cold, structured gas, especially along filaments where cores form and collapse. The densest regions are where gravity has the best chance of winning, and filaments provide natural pathways for gathering and focusing material. When you step back, this means that bright stars often begin in places that are dark, cold, and carefully organized by invisible forces. And with that thought, you can let the ideas settle quietly, like distant light forming far away, while everything else grows softer and still.